How are you?
Great, ma'am. I
Oh,
have some questions about the special homework. So first of all, I wanted to say that I've been using the class notes to do the homework. And yeah, so if you look at my homework and you see like some notes that is the same you wrote, I'm just using some of the class notes to do my homework. And the second thing, I want to send you a picture of it. It's for question 5. I got to the disproof, and it's when I did the consider m is 2 and consider n is 8. Is I don't know how to put it together to prove that it's not a perfect square. I know what I'm doing, but I just don't know how to like put it in paper.
okay, I can help you with that.
Yeah. Okay.
All right, I'm going to pause the recording for just a minute and put the camera to the paper.
All right.
All right, so first let's check our focus. You tell me if the focus is good. Is the focus good?
It is. Yes.
All right, so you're working on special homework 5, number 5, correct?
Mhm.
Can you read the statement that you're going to disprove? Can you give me the original statement?
The original statement is the original statement is oh,
You should write it on your homework too. I'll also look it up.
oh,
What?
okay. I'll
It's
have to
okay.
revise it. Okay. The original statement is universal quantifier M N
So does it look like this for all M,
N
N?
yes, yep. Belongs to Z, belongs to real
Okay.
numbers, yeah. Integer, sorry. And if Mn is a perfect square, then M and N are perfect squares.
So if the product MN is a
Yep,
perfect square,
yep.
then M
And
and
N,
N are
yeah.
perfect squares.
Yes. Ma'am, you're not recording. Oh, you're recording. Yes. Yeah, 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 you're recording.
Thank you so much. So that's the original.
Yes.
Great. And uh, is this one where I asked you to decide if it's true or false by looking at some examples?
Yes, it is. And
Hmm.
I I am doing the false version. So
That's correct because if you poke around, you can find an MN that's a perfect square
but
where M and N are not both perfect squares, right?
yep.
Right. So in fact, now tell me, does the red show up okay, or is
Yes.
the red
The
is
red
okay?
showed up good, yeah.
So there exist M and N in
Mm-hmm.
Z such that here's our here's our P, right?
Mm-hmm.
P of M and N. And here's our Q of M and N, right?
Mm-hmm.
So we want P and not Q. So such that MN is a perfect square and, or we could say, but M is not a perfect square or N is not a perfect square or both because we use the inclusive or, right?
Mm-hmm.
Great. So to prove this existential statement, let's just review what is required in general when we are going to prove an existential statement. First of all, this will be called a counterexample because we're going to use our proof of this existential statement, and all we need is an example to prove an existential statement. We're going to use our proof of this negation of this existential state, of proof of this existential statement to
Mm-hmm.
disprove the original universal statement.
Mm-hmm.
Right. So you did some scrap work, right?
Yeah, so it's assume MN is a perfect square.
Mm-hmm.
You wish to know M and N is not a perfect square.
So what did you try for M and what did you try for N? And then
For
what was MN?
M, I tried 2, and N, I tried 8, and MN was 16.
So 16 is a perfect square.
Yes, but M is
These are
not.
not.
Yes.
And I did give you a hint, and the hint to show, you know, M is not a perfect square. And I know there's a lot written in the special homework, but I did give a hint. Uh, show that the square root of M is not an integer.
Oh,
And we know that square root of 2 is not an integer. And
yeah.
in fact, square root of 8 is not an integer either. You actually don't need both of these to not be perfect squares. But in fact, if one of them is not, the other one won't be either. This
Mm,
is a perfect square because the square root of 16 is an integer, namely 4. So this is great. This is going to work for our counter example. We're going to counter the claim that the original was true.
mm-hmm.
Hey, Isaac, I'm glad you're here. I hope starting a little
Hey,
later
Professor
helped.
Good.
Yeah, I thought starting a little later might help a little bit.
Yeah. Thank you. I appreciate that.
Sure. So let's just review before we write this counter example. Let me just review with you how we prove an existential statement in general, and then we can look at those notes when we work on this, okay? And this is in class notes, but we can review proving an existential statement because that's what we're going to be doing. We're going to be proving that existential negation, right? So here's the general form.
Do we start with consider?
Well, we will do, yes. But first, I'd just like to review the general idea for proving any existential statement. And you're right, I often start with consider because you've done this scrap work, you've thought about it, and you are asking your reader to consider your thoughts. So, yes, consider is a great way to start the counterexample. But let's just review the general form of an existential statement. I'm getting a big storm here. There's a tornado watch here in Baltimore, so I hope our internet holds on. In fact, this will be an existential statement with two variables because we have two variables in this particular problem, right? M and N. So the general form would be something like this. There exists an X in some set D. There exists a Y in some set F such that some property holds for X and Y. Okay? That's the general form. So for us, it's there exists an M in the set of perfect squares. We'll call PS the set of perfect squares just for comparison here between the general form, and there exists an N in the set of perfect squares such that MN is not an element of the set of perfect squares. Do you see how the general form applies to our example?
Yeah.
Okay, so the general rule or the rules for this kind of proof are two things. Well, first, step zero, do scrap work, find your values. Okay. And then one, we verify our values reside in the correct domain. And then two, we verify the property. But I think I wrote the property wrong here because in fact, here there exists in uh I wrote the property wrong because the property well, this is the property. I've just rewritten it a little bit, but this is wrong. We want this is wrong.
Okay.
I'm sorry. Okay, because it's let's look at the statement. It's that MN is a perfect square. Okay, so let's do this right. So there exists an M in Z and there exists an N in Z such that, and the property is a compound property. It's that MN is a perfect square. I'm not even using I'm not even using this anymore. I'm not even going to use this because I think it just confuses the matter. See, even an old pro like me can make a mistake. And M is not a perfect square. What is it, M or it's M or N? Okay, so let me fix that. And M or N is not a perfect square. Is that what we're trying to prove?
Yes.
Okay. So we're going to verify that our values are integers because they have to be integers. And then we're going to verify the property, and the property is that MN is a perfect square and either M or N is not a perfect square. So let's just do that. Just follow these rules. So you want to consider, right? You said consider. You tell me what to write.
Consider M equals 2
Yep,
and N equals 8.
yep. And they have to be integers, right? So we'll just say that. Clearly they are integers. Clearly, this is one. M and N are integers. And the second part is to verify that MN is a perfect square. And then the other thing we have to do in the second part to verify P of MN, this predicate, is that either M or N is not a perfect square. And we can use our hint.
So we square root 2.
Yep. So notice MN is 2 times 8, right? Is 16. And to show it's a perfect square, we just have to show it's equal to x squared, right? For an integer x. It's equal to 4 squared, and 4 is an integer. That's the definition of perfect square. Mn is a perfect square if it's equal to x squared for an integer x. And it'll be a positive integer x. So Mn is a perfect square. We've got halfway done. And now you just look at square root of 2. But square root of 2 is not an integer, so 2 is not a perfect square. And you can just leave it at that. Of course, 8 is also not a perfect square, but look what we have to show. That M is
M
not a
is not a
perfect
perfect
square
square
or N is not a perfect square. You actually don't have to
to
prove
show
that
both
both
of
of them
them.
are. It's enough. So I'll just put a little note. This is enough
All right. Because I
to,
knew how to do it, but I didn't know how to put it into paper.
you just say, you look at the square root of it and
Mm-hmm.
you say, hey, that's not an integer. Square root of 2 is not an integer. See, square root of 16 is an integer. It's 4. Square root of 36 is an integer. It's 6. That's why 36 is a perfect square, right? Square root of 100 is 10. That's why
Mm-hmm.
100 is a perfect square. But 2 is not because square root of 2 is not an integer. So if you go back and read carefully in the special homework and look for that hint, I think you'll see it now. But there was a lot there.
Yes, it was notice n equals 5 is not a perfect square because square root 5 is not an integer.
That's right.
Okay.
Okay. This is enough, but it is not wrong to also notice square root of 8 is not in Z. So 8 is not a perfect square. You don't need that. You could do one or the other. You don't need both.
Mm-hmm.
Generally, I say don't write more than you need to write. So, Isaac, I don't want to see you turning in this particular counterexample. I want you to find your own M and N so that Mn is a perfect square and M or N is not a perfect square, but you'll be able to do it now that you get the idea. The bottom line is we have to pick factors that multiply together to make a perfect square, but the factors are not perfect squares. And there are lots of other ways to do this, okay? So pick elements other than 2 and 8, Isaac, when you do this problem, okay? I hear you thinking, but it'll be good for
Uh,
you to find your own.
okay,
All
I
right.
got you.
Okay, good. All right, so Isaac, it's your turn for a question.
Can I ask for help with the special homework?
Yes.
Like, I'm just, I guess, like, to break down, like, just starting with 1A. Like, do you think you could, like, explain, like, how we go about knowing, like, how to turn that into a conditional statement?
Right. In general, uh, this is the idea. I'm going to share my screen because there's some general things going on. Okay, so it talks about the product of two odd numbers is always odd. So what is the domain of the numbers that we're dealing with?
Is it odd?
Yeah, we're talking about odd numbers.
Okay.
And that's going to be your key to figuring out how to write a universal statement in if-then form, as a conditional. If you just realize that if we make the condition to be so that we're forcing the numbers to live in this domain of odds, then the result will follow. All right. It's all about figuring out what the domain is. And that domain should be the condition. Once we have the numbers in that domain, the result will follow. So if, X and Y are odd, all right, so now we've got ourselves two odd numbers. You see what I mean? So we've made membership in the domain our condition. It's the hypothesis. That's called the condition. Membership in the domain of interest. Here it's the odds. Becomes our hypothesis. But the hypothesis is also called the condition because it's a conditional on the condition that X and Y are odd. And what is the result that that statement says, Isaac?
It should be that AB is always odd.
AB.
I mean, then XY is odd.
Is it the product? Yeah, yeah. And if we were using A's and B's, you would say AB. But if X and Y are odd, then XY is odd. See how that works to write that as an if then?
Yeah, yeah. I think the domain concept kind of helps me understand it better.
And there is a video from Monday night's office hour, and we go through this problem almost entirely in that office
Oh,
hour.
wow.
Okay.
Oh, okay.
Do you have another question?
Yeah, I was also wondering about if we could look at 1B.
1B?
Yeah.
No, I'm going to refer you to the video.
Okay. All right, then I'll take a look at that then.
Okay, so do you have questions on, you really haven't had a chance to look at these yet, have you?
Nah, I really
Yeah.
was just about to just try to work through it with you. But if you're saying there's an office hours where you work through the whole thing, then I'll just take a look at
Well,
that.
no, we're not going to work through the whole thing, but I will give you pointers. Let's look at problem 2. You can watch the video on problem 1.
Okay. I think my main thing is really just like how like writing the proofs is kind of shaky for me to like pick up because it just feels like the words are just coming out of nowhere. Like I'm not really understanding like where.
So let me ask you this. Have you found the book yet? Have you found the link to the book in WebAssign yet?
Yes, I haven't looked
Oh,
at it though, honestly.
well, honestly, I told you last Thursday that you needed to read section 4.1 and 4.2. If you're having trouble with the words, part of the way that you overcome that trouble is by learning something. You learn something by reading sometimes.
Yeah.
The other option is to look at the class notes because in the class notes, we work through numerous proofs. First, we went over the definitions, remember?
Yeah.
Trying to get out of my own way here. So first, you have to know the definitions. You'll want to keep those handy. All right, so these are the general guidelines for proving existential statements. That's this part. And then the guidelines for proving universal statements. That's this part. And then we have some examples. So to prove an existential statement, you want to do some scrap work. To prove there exists a prime number p such that 2 to the p minus 3 is not prime, the big hint is keep it simple and keep your examples small. So we started with p equals 2, and we plugged 2 into p, and we found out that 2 to the p minus 3 is 1, and 1 is not prime. So we found it already. So now, how do you write it up? Tell your reader when the proof is starting. That is the first step. You need to read section 4.2. If you don't have time to read both, read 4.2. The first thing that the Dr. Epp will tell you is you have to tell your reader where the proof starts. Then consider, and now we found P equal 2. So that's a good way to start that proof. We're not assuming you could, but it's sort of better to say, hey, consider P equals 2. Notice, and then you explain why 1 and 2 work out. Now, what are 1 and 2? They're right here. Step 1 for proving an existential statement is to verify that the X that you found is in the right domain. And part 2 is to verify that the predicate, which is the property, holds. It's just 2 steps. So here we want P to be a prime. Do you see that? It has to be prime. So we discuss why 2 is prime. Well, we look at the definition of prime. 2 is prime because 2 is bigger than or equal to 2. A number n can only be prime if it's bigger than or equal to 2. So 2 is big enough, and its only positive divisors are 1 and 2. That's the definition of a prime. X is prime if X is bigger than or equal to 2, and its only positive divisors are 1 and 2, or 1 and X in the case of X. And then the property is that 2 to the P minus 3 is not prime. So we look at 2 to the P minus 3. It's 1. And we explain why it's not prime. It's not prime because 1 isn't even big enough to be prime. It's not greater than or equal to 2. That's why it's not prime. Negative numbers can't be prime. They're not big enough. 0 can't be prime. It's not greater than or equal to 2. But there are numbers that are big enough that still aren't prime. That's why I gave you example 2. Let's look at that. It says almost the same thing. It says prove there exists a prime number P such that 2 to the P minus 3 is composite. Now there's a difference between not prime and composite. 1 is not prime, but it's not composite. It's not big enough. Let's look at the definition of prime and composite. An integer, here's our definitions. An integer P greater than or equal to 2 is prime if its only positive divisors are 1 and P itself. Okay? Now, an integer N greater than or equal to 2 is composite basically if we can factor it in a non-trivial way. What do I mean? I mean, if there exist integers a and b such that n is equal to a times b, so we can factor n into a product a times b, and both a and b are bigger than 1. So for example, think about 5. How can you factor 5 into a product of 2 integers? There's only one way to do it. It's 1 times what?
Um, to factor 5 into two integers.
Yeah, there's only one way to do it. It's almost a
Um,
trick question.
1 and 5.
Yeah, and you see, 1 is not bigger than 1. 5 is, but both factors have to be bigger than 1. 1 needs to be less than 1, and 1 needs to be less than 5 for that to be what we call a non-trivial factorization. 5 does not have a non-trivial factorization because we can only factor it into a product of 1 times something else, namely 5. So 1 is not composite. I mean, 5 is not composite. 1 isn't either, but 5 isn't composite. It's big enough, but it's not composite. Let's think about 6, though. Can you factor 6? into a product of two integers a and b where both the integers are bigger than 1?
Yes.
What would those integers be?
2 and 3.
Exactly. 6 is composite. What about 8? Is 8 prime or composite?
Yes. That would be 2 and 4.
You get the idea?
Yeah.
So that's what we're trying to do here. We're going to have to factor 2 to the p minus 3 to show it's composite. So we tried some primes. We knew that p equals 2 would not work out because it made 2 to the p minus 3 equal 1. So we tried some other primes. We just started low and just worked our way up. When p is 3, 2 to the p minus 3 was 5. That's not composite. 5 is prime. When p was 5, 2 to the p minus 3 was 29. That's prime. You can't factor it either. But when we tried p equals 7, we got 2 to the p minus 3 is 128 minus 3, and that is 125, which is composite. So let's look at how we write it up. We found 7 to work. So proof, consider p equals 7. We have 2 steps. We have to verify that the number p that we picked is prime, and then we have to verify the property that 2 to the p minus 3 is composite. So let's look at how that's written up. So notice, 1, 7 is prime because 7 is greater than or equal to 2, and its only positive divisors are 1 and 7. So 7 is prime, and that's what you have to write to verify that it's prime. You can't just say 7 is prime. You have to talk about its divisors only being 1 and 7. And 2, we need to show that 2 to the p minus 3 is composite. Let's look at that. So here we show the work. 2 to the p minus 3 is 125, and we factored 125. Do you see how we factored it into 5 times 25? These are what we call non-trivial factors. They're both bigger than 1. So we just verify 5 is an integer and 25 is an integer. That's part 1 of the definition of composite, is that we're picking integers a and b. Showing that 125 is a times b is actually part 2 of the definition of composite. And the third part is just to say, hey, 1 is less than 5 and 1 is less than 25. So both a and b are larger than 1. So 2 to the 7th minus 3 is composite by definition of composite. So you can look at the class notes as really helpful guides for how to write proofs. Then we had some things that we may assume without proof, the closure properties of Z, sums of integers or integers, differences of integers or integers, products of integers or integers, and the zero product property, the ZPP. We talked about those in class yesterday. You were there. So now let's change to proving universal statements. Now think about this statement. Prove the sum of 2 even integers is even. The first thing we're going to try to do is write that as an if-then. So what is the domain that we're shooting to try to make our condition? We're going to write this as a conditional. So we're going to try to milk the domain. What is the set that these numbers need to live in? What kind of integers are we looking at?
2 even.
Yeah, they're even. Okay, so we're talking about numbers being even, and if they're even, then their sum is even. See what I mean? So the domain that we're going to use in our hypothesis of our if-then is the evenness. So we're going to write it as an if-then. If a and b are even integers, then A plus B is even. See how easily that works when you get the trick of using the domain as your if part? And why do we even want to write this as an if then? Because we need to get our eyes on the hypothesis. That's what we're going to assume. We have to know what we will assume. We have to know that. We can see it here. A and B are even integers. That's what we will assume. You can just say assume A and B are even, or you can assume A and B are even integers. What do we wish? You see, we need to know what we wish. We wish to show A plus B is even. That's our wish. So we use our thinking notes to write our wish. I know you're tired, you've had a long day. But what I'm trying to show you is write it in if-then form using information about the domain. What kind of numbers are they? Figure out what your hypothesis is. It's the if part. Assume that. Figure out what you wish. That's the conclusion, the then part. Then use the definition of even. It's got two parts. Both parts of the definition of even are necessary. And revisit your wish. What does it really mean to show A plus B is even? Oh, A plus B has to equal 2 times M, where M is an integer. So we proceed to get that done. So we look at A plus B. We use these part 1 definitions and substitute, factor out the 2, and suddenly we have A plus B equals 2 times something. That something is going to be our M. Then we have to address the fact that M has to be an integer. How do we do that? We use the facts that K and J are integers. Since K and J are integers, their sum, M equals K plus J, is also an integer because sums of integers are integers. So A plus B equals 2M, where M is in Z, and that means it's even. So you've got another example that we did in class, and we just discussed if you want to disprove a false universal, you'll prove its existential negation. We just did that a few minutes ago in that problem that Karen asked about. It's called giving a counterexample. To disprove a false existential statement, we prove its universal negation. So in example 4, I give a false existential statement because I wanted us to practice another universal proof. Also, I wanted us to practice disproving a false statement. So the statement, can you read the statement here? Can you see it?
Yeah.
Why don't you read this false statement?
It says there exists a positive integer n such that n squared plus 3n plus 2 is prime.
Great. So if we're going to disprove it, we know we need to see the negation because we're going to be proving the negation. All that practice with negating quantified statements is being used now. So instead of there exists a positive integer n, in the negation, what happens to there exists?
That turns into a for all.
That's right.
Yeah.
For all positive integers n, and instead of n squared plus 3n plus 2 is prime, the negation of that is that
N squared plus 3n plus 2 is not prime.
right. So we're going to prove for all positive integers n that n squared plus 3n plus 2 is not prime. So we wrote it as an if then. What kind of integers are we talking about?
Positive.
Yes. So use that for your hypothesis. If n is a positive integer, then n squared plus 3n plus 2 is not prime. And now we know what we're going to assume. We're going to assume n is a positive integer. That's all we're going to need. And then we're going to show that n squared plus 3n plus 2 isn't prime, we're actually going to show that it's composite, that we can factor it into two integer factors, both of which are bigger than 1. So assume n is a positive integers. We wish to show that n squared plus 3n plus 2 is not prime. So we're going to look at n squared plus 3n plus 2. Guess what? It factors into n plus 2 times n plus 1. It doesn't matter what order you put these, but you do have to be able to factor a quadratic. So one of these will be our A, and the other one will be our B. This is part two of the definition of composite, that our expression, whatever it is, can be factored into A times B. Now we want to figure out that these are integers. Well, n is an integer, so we're using those closure properties, things we may assume without proving. Since n is in Z and sums of integers are integers, A equals n plus 2 and B equals n plus 1 are integers. You just have to say it. When we add integers together, we know that the result is an integer. So we said that. So that's part one of the definition of composite. You see, if we go back and look at the definition of composite, an integer n is composite if it's bigger than or equal to 2, and there are integers a and b such that n equals a times b, and 1 is less than a and 1 is less than b. In fact, if 1 is less than a and 1 is less than b, n will automatically be bigger than or equal to 2. We're going to find out this expression is bigger than or equal to 2 here, because when we factored it, we factored into n plus 2 and times n plus 1. They are integers. Now we got to show they're both bigger than 1. How do we do that? Well, now we're going to use the fact that n is a positive integer. What does that even mean? Well, it means n is bigger than or equal to 1. So the smallest n can be is 1. So what does that tell us about this factor a? A is n plus 2. But that's bigger than or equal to 1 plus 2 because n is bigger than or equal to 1. You see how that works? So A is going to be bigger than or equal to 3. That's definitely bigger than 1. So A is bigger than 1. And B is n plus 1. But again, the smallest n can be is 1 because it's a positive integer. So n plus 1 is bigger than or equal to 1 plus 1. Well, 1 plus 1 is 2. So the smallest b could possibly be is 2. 2 is bigger than 1. So we just proved that A is bigger than 1 and B is bigger than 1. And then we can go back and say, oh, that means n squared plus 3n plus 2 is bigger than or equal to 1 squared plus 3 times 1 plus 2, which is 6, and that's definitely big enough. So it's composite, and that means it's not prime, because a number cannot be both prime and composite. A number that's bigger than or equal to 2 is classified as either prime or composite. So these are examples of proofs that are written up that you can refer to, and that's just from last Thursday. And I gave you some due later problems. One of the things you need to do, I know you're a busy, busy man. I know this. But you really need to read the class notes within 24 hours of class before you forget the things that were discussed in class. And you need to do the due laters that are given, because that will reinforce everything. And then we have notes from yesterday. Those notes are also really, really good because we kept doing more proofwriting so that you would have more examples. In example 1, I give a false existential statement and we prove its universal negation. And here are the steps. We wrote the negation, then we wrote the negation as an if-then because the negation was universal. That way we got our eyes on our hypothesis and on our conclusion. This statement looks a lot like one of the statements from homework, but it's not the same statement, is it, Karen?
No, it's not. It's totally different. I was
It
using
re-
it as an example, actually.
that's right. It's yes. It's it's the converse of the false statement that was given in problem 5. But
Yeah.
you can read through these proofs, Isaac. You really have got to make use of all of these good class notes because I walk you through and I even identify when the different parts of the definition are being satisfied so you can think about and go back and look at the definition. Here it's the definition of rational. You can go back and look at the definition of rational, which we gave right here in these notes. And it's a three-part definition. So if you're asked to show something is rational, you have three things you have to do before you can say, yes, that is rational. Okay, so the class notes are a great place to start. I gave some do laters.
Ma'am, I'm sorry to cut you off, but I have to leave office hours.
Well, let me then let you go ahead and ask any other question that you have. And David, Alyssa has joined us, and I want him to have a chance. But again, you can watch the Monday, March 9th video of office hours for problem number 1 because we practically worked the whole thing. Karen, did you have another question you needed to ask?
No, ma'am, that was my main issue. I'll continue the homework by myself and your notes.
Well,
Thank you.
well, you did a really good job coming to office hours Monday, uh, and getting a head start because this homework, I didn't I tell y'all in class last week to be sure and give yourself 3 or 4 hours to work on this homework? I did. I'm sure I did. Okay. So thank you. You're excused. You may leave at any time, but I appreciate your telling me you have to leave.
Thank you, ma'am. Have a great night.
Thank you too, Karen. It's always a pleasure to see you. Hi, David. Do you have a question?
Sorry, I'm also leaving as well. Thanks for the help though, Professor.
Isaac, you're welcome. Please read the notes, read the book, read the
Gotcha.
book,
Will do.
okay? And
Will do.
watch, okay. I think it'll really help you with the wording because it's not something you're born knowing how to do. Get a good night's sleep, okay? And
Okay.
then when you wake up, you'll have 7 hours to work on this, okay?
Okay.
All right. If you want, tomorrow morning, it is possible that I could give you an office hour at like 11 a.m. If you want, you can email me in the morning.
Okay.
If it's possible, I'll do it.
All right. I'll be in touch then.
Take care.
Okay,
Hi,
you too.
Thank you. I will. Hi, David.
Hey, Professor,
How are you?
I'm good. I just wanted to join office hours because I need help with the event. I'm currently doing the homework too, and I just need help with the last part, like the part says it was like since A and B or it's like let me show you actually.
Are you having trouble writing statements as if-thens, as conditionals?
No, not that part. It's more of like I don't know if you can see it.
Can you take a picture of that and email it to me so that I can look at it?
Okay, yeah,
All
I
right,
got
you
it.
do that. I'm going to pause this recording, but make sure I start the recording again after I get your email, okay?
Okay,
I'm going to take a 1 minute break. I'll be right back
all right,
while
thank
you
you.
do that. Perfect. Can you hear me?
Yes, ma'am.
I got it. It looks good. Let me give you some suggestions.
Okay.
Okay. So what number was this?
Number two.
Number two.
Yeah. Like the I just don't like I don't know how to really put
I'm,
the
I'm going to
last
help
part.
you. You,
Appreciate
you,
it.
you did nicely. Okay. So you said proof begins here. That's good. And you said consider P equals 5. That's perfect. And then you went to justify 1. You did perfectly. You
Okay.
explained exactly why 5 is prime. You even said 5 is greater than or equal to 2, and its only divisors are 1 and 5. That was perfect. I'm going to
Okay.
help you with part 2. Okay?
Okay.
All right. So notice I'm going to start the sentence with a word. Okay? Notice, and so you look at 2 to the 5 minus 1, whole thing minus 1. So it's 2 to the 4th minus 1, and that's, of course, 15. Now, let's review together the definition of composite. All right. An integer n greater than or equal to 2 is composite if 1. There exist integers a and b such that 2. N is equal to a times b, and then 3. 1 is less than a, and 1 is less than b. So I think you almost got it. You certainly showed that we're getting a composite number, but you need now to give me the integers a and b and show that n equals that a times that b. State that they're integers, show the factorization, and then simply say, hey, one is less than one of them and one is less than the other. And I know exactly the A and B you're thinking about, right? So you can say, you know, note 15 is equal to, your A times your B, right? Which are the two factors you're thinking about?
5 and 3.
Yes. 5 times 3. So that's part 2 done. You've got n equal a times b. See, it's helpful to check this list off, right? You got that
Okay.
one. Notice 5 is an integer and 3 is an integer, right? Just say it. There's nothing to prove there. You just say it, right? And then finally, okay, well, you simply say 1 is less than 5 and 1 is less than 3. So 15 is composite by definition, and you're done. So what's the lesson to learn here? The lesson to learn here is you have to refer to the definition. You did very nicely when you verified that P was prime. I know you looked at the definition of prime, didn't you?
Yeah, yes, ma'am.
Well, to verify that something is composite, you have to look at its definition, and that's a 3-part definition, okay?
So basically, I'll have to do the same thing for the rest of them too, like the rest of the homework problems.
Well, every homework problem will be a little different because
Yeah,
they use different um, definitions. You were here in the office hour when we were looking at the class notes, right?
a little bit towards the end.
Well, let me just show you again how much is there for your edification. The last 2 days of class notes are nothing but the definitions and a gazillion proofs.
Yeah.
And if you carefully read these, you will see the steps that we take, right? If it's a universal statement, like here we're disproving a statement. So we wrote the negation, but then we wrote the negation as an if-then. You always want to write your universal statement as an if-then statement. Why? Because we need to see what we're going to assume, and we need to see clearly what we wish to prove. And here, the idea is that this statement is about perfect squares. So the domain is perfect squares. So we put that into the hypothesis. We just use that as the condition. If M and N are perfect squares, then this good stuff happens, you see. Mn is a perfect square. So you look at the domain of the objects, that membership in that domain becomes the condition. It becomes the if part. It becomes the hypothesis. And here we go through exactly what it took to prove that M times N is a perfect square. We showed it looked like something squared, and that something, we called it W, is an integer. And that's all a perfect square is. Mn has to equal W squared, where W is an integer. That's why not only do I put my first wish, we wish to show Mn is a perfect square. That gets me started. I realize I'm going to have to look at M times N, right? But then I dig into the wish a little more and I actually write what it's going to take to prove that Mn is a perfect square. How did I know this? I went back to the other day of notes and I reviewed the definition of a perfect
Of a
square.
square.
Yeah, and that this first page of definitions is critical, right? An integer x is a perfect square if, and there are two parts here, x equals n squared, and then the second part is that n has to be an integer. Because if, x equals pi squared is not a perfect square, not because this part fails, but because pi is not an integer. X equals square root of 2 squared isn't a perfect square because square root of 2 isn't an integer. So refer to your definitions, write these definitions out, and keep them on a piece of paper separately. All of this page is just like the general ideas. I think you've definitely looked at this because I saw that you followed the 1, 2 steps for
Yeah,
proving, yeah, you did a nice job with that. And then, of course, proving a universal statement is a little more involved, but we've got lots of examples of proving universal statements. We've got our first one here is example 3. We did example 4. We're disproving an existential, so we wound up proving a universal because its negation was universal, right? And this was about proving something's composite, and it was quite involved. But I gave some do later problems. So,
yeah,
definitely use the class notes. Do you know how to get into the ebook?
yeah, I do actually.
Yeah. Well, remember I wrote several times on the notes yesterday and last Thursday that you really need to read
Yeah,
section. Yeah, you really do. Uh, and I was hoping that that would have gotten done, you know, over the weekend
yeah,
because it takes some time, but it's helpful.
for
I hope
sure.
I hope this helped.
Yeah, it did. It's just um sometimes I'm having a problem like with the ending, like sense, like what you just showed me right now.
But if
Just
you
like
look at the examples of
yeah,
all those proofs, you're going to see it. Like the last thing I do is I just sort of give a closing sentence. So 15 is composite. That's what we were trying to prove. You started it beautifully. Consider P equal 5. You verified P was a prime. You got this far, and then you forgot that you need to look at the definition of composite
yeah,
to make sure you address it. And then just remember, what was I trying to do? Look at your wish. We wish to show that 2 to the P minus 1 is composite. So at the end, you can say that it is composite.
And also, about tomorrow, the quiz, is it just like knowing the definition and like
Yeah. It's going to be a fill in the blank.
fill in the blank? Okay.
In fact, I'm going to send an announcement right now to remind everybody that we will have a quiz tomorrow on definitions.
So it's not proven, it's just knowing the definition of everything.
It's not for what?
It's not proven, it's just like knowing the definition, like how you, like what you just showed me in the notes.
I might have one question where I give you an if then and ask you what would you assume and what would you wish. I might just do that, but no, you won't have to write a whole proof tomorrow. Over spring break, you're going to get another special homework that's going to give you lots of more practice,
Yeah,
right? Of writing these proofs. It takes time. That's why I gave you so many do later problems, because the more practice you get, the easier it gets, the
yeah,
faster you can do it. Because when you sit for the test, there's only so much time. But practice, I mean, you're a sports guy, right? You play soccer, right?
yes, ma'am.
How did you get good at it?
Practice, practice, practice.
And it's the same with math. And in fact, there is muscle memory in mathematics. It's visual, like you watch yourself, and then you realize, oh, definition, definition. Oh, we wish to show. And honestly, it gets easier.
Yeah.
Okay. So it is possible that I might be able to give another office hour tomorrow at 11 before I leave for work. I'm not sure because I'm waiting for a phone call, an important phone call. But if I get that phone call earlier and someone emails and asks, we could have a last minute office hour tomorrow morning if I can possibly swing that. Okay.
No problem.
Okay.
Thank you so much for helping.
I'm so glad. I'm so glad that you came into office hours. I hope to see you more. You can always ask for office hour at another time as well.
Is it
But
possible to do like office hours during the weekends? Because I feel like that's when I'm mostly free.
yes, Saturday afternoons, Sunday late afternoons, sure.
Okay.
I don't mind at all. We could even do this weekend.
No problem. I'll definitely email you about it just to remind. And then,
Okay. Well, I have to work to get that next special homework ready for you.
thank you so much, Professor.
You're very welcome. Good night.
Good night.